Hello, welcome to the Wednesday lecture. So let's begin where we left off from Monday, which was this slide here. And let me make this full screen and bring up the laser pointer. So if you remember, we represent our pipeline consisting of instruction fetch, which is getting an instruction from the location pointed to by program counter, and then doing decoding of the instruction as well as reading the operands from the registers, making those operands available to the ALU for execution during the next phase. And then if there's memory operations involved, then we carry out the memory operations in the following phase. And finally, we'll write back the results of either memory access or ALU operations back into the register file. Also remember that these two units, the ID and WB, write back and decode and read of registers, are basically the same unit, but they are broken into two halves because writes always take place during the first half of a cycle and reads always take place during the second half of a cycle. So basically, these two units are the same. So in fact, what we have is we have a four-stage pipeline. We have IF, and then ID, execution, memory, and write back, which is the same as writing back into the register files or operating on the register files, but we are doing it at different cycles. So with this in mind and this convention that we're going to use for the future, then let's move on and talk a little bit about pipeline performance, and then we'll come back and talk about the pipeline hazards and other pipeline operations. So let's assume that a stage of a pipeline takes 200 picoseconds to carry out. However, for for register reads and register writes, because we only write in a half cycle and we only read during a half cycle, then those operations take 100 picoseconds to complete. So it's kind of like dividing our stages into four stages, but one of them is carried out in two half stages, which ends up looking like 5 stages, but in fact we have 4 stages to operate. That'll make a little bit more sense as I go through the examples. So for single cycle data path, let's take a look at different instructions. For load, which takes the longest, we go through the fetch, register read, ALU operations to carry out the calculation of the effective address, memory access, and then finally writing back into the registers. So these operations take 200 plus 100, 300 plus 200, 500 plus 200, 700 plus 100, 800 picoseconds to complete. So that's for load operations. Now for a store, the operations we carry out are instruction fetch, register read, ALU operation, and memory access, but we are not writing back anything into the registers. So if we are going to do store all by itself, it would take, and sequentially, it would take 700 picoseconds. Similarly, R-type takes 200, 300, 500, don't have any memory access, 600 picoseconds to complete. Branch equal to only takes 500 picoseconds because we do fetch the branch equal to instruction. We fetch the registers in order to compare them, and we perform the ALU operation to see whether they are equal or not. But notice that we're not paying any time penalty for calculating the target address. And the reason is that computation of the target address is taking place in parallel with the ALU because we have two different adders. We have one ALU, one main ALU, and then we have an additional adder. And because they operate in parallel, then we don't pay any time penalty for calculating the target address. And that's why branch equal to takes 500 picoseconds. Now, as I said before, for a single cycle data path, the length of the clock cycle is decided by the slowest operation or by the critical path. So in this case, the slowest operation is load word, which takes 800 picoseconds to complete. And that decides the length of the clock cycle for single cycle data path. So even though these other instructions take less time to complete, the length of the clock cycle still would be 800 picoseconds for our single cycle data path. So the operations for the single cycle would be like this. We still go through these operations. We still fetch an instruction. We read the registers. We perform ALU. We access memory if needed. And we write back into the registers if needed. That takes us 800 picoseconds. So first instruction completes, then the next instruction begins. But notice that even if you don't use, like for example, if this is an add instruction and you don't use the data access part of the add instruction, which we don't have any data access for memory, still it takes 800 picoseconds to complete that add operation. And then similarly, it continues and instructions are executed sequentially, each one taking 800 picoseconds to complete. Now, let's see what happens in the case of the pipelined operations. Now, pipelined operations, again, remember that we basically have four resources. We have instruction fetch, we have register read and write, which is divided into two parts. The read part is here, the write part is here. Okay, but it's the same resource, it's the same register file. So in effect, we have four stages or four resources for our pipeline, but one of them is divided in half and is used at different half cycles, resulting in a pipeline that looks like it has 5 stages. So in the case of the pipeline, we get the first instruction, we fetch it, we get the operands for it, we perform ALU, we do data access if needed, and then we write back if need be. While all of that is going on, and in the second stage, we begin fetching of the second instruction while the first instruction is being executed. And the second instruction goes back one step behind the first instruction during its execution. Okay, and it completes. And then similarly, we get the next instruction at the third stage. And so now things are happening in parallel in 3 stages: ALU, register read and write, and instruction fetch. So as instructions come in and the pipeline fills up, then we get into a situation that once the first instruction completes and the pipeline is full, then we begin completing the next instruction in the next cycle. So if the first instruction finishes here, then it takes 200 picoseconds to complete the next instruction, or one cycle. Then similarly, when this one completes, the next instruction finishes in the following 200 picoseconds, or the next cycle, and so on and so forth. So like the example that I showed you for handling or doing loads of laundry, then in here we finish instructions instead of finishing loads of laundry at every cycle once the pipeline is full. Okay, So in that case, the execution time for instructions is 200 picoseconds, which basically means that at the end of each cycle, we can produce one instruction. Here, 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 and so on. So let's see if we can formalize now what the performance of a pipeline looks like. Let's assume that all the pipeline stages are balanced, meaning that they all take the same time. If things are unbalanced, then the operations of the pipeline becomes a lot more complicated, and speed ups would be a lot less. So if the stages are balanced, then the time between instructions that are pipelined is equal to the time between instructions that are not pipelined divided by number of stages. Okay, which basically that's telling you is that however long it takes to do the entire operation, now when you go to pipelining, you can finish that once you finish one stage of the pipeline. So if you divide the total time by number of stages, that basically gives you the time per stage. So in our case, we have the time of non-pipeline as 800 picoseconds. Number of stages is 4. Again, remember that registers read and write happen in the same resource and in the same complete cycle, but they happen during different half cycles. So we get 200 picoseconds as the time for completion of instructions or time between instructions in the case of the pipeline operations. Now, if you look at the speed up would be the time of non-pipelined operations. In other words, we haven't optimized anything, our old time, divided by time of optimized or improved operations through pipelining. So in that case, if I replace the time of the instructions, between instructions pipeline, in this formula with its definition in this formula, then the time between instructions non-pipelined would cancel each other out, and the speed up would be number of stages. And in our case, number of stages is 4, therefore the speed up would be 4. Now, notice that one implication of this formula is that you can actually improve the performance of your operations by adding more stages to your pipeline. In other words, the more stages you have in the pipeline, the shorter your time of pipelining would be, and the bigger your speed up is going to be. But the problem is that as you add number of stages to a pipeline, then pipeline operations will become more complicated, as we'll talk about pipeline hazards later. So let me stop here, and then I'll continue the discussion in the next video.